Hi, everybody. This is going to be slideshow number 1 of module 2. We're going to talk about the probability distributions and some properties and stuff like that. So the first thing I'm going to do is introduce you to the basic regression model. So pretty much everything we're going to do this semester is going to take on some form of this. So we're going to have some outcome called y, um, indexed by I. So in other words, you can think of this as some outcome. Let's talk about housing prices. So house I is going to run from 1 to n. Capital N is going to be our sample size. So we're going to have some sort, maybe we'll have 5,000 home sales. And we have little pieces of data like the neighborhood it's in, we have the number of bedrooms, we have the square footage, and so on. We have some information about the house, and we're trying to figure out how to predict housing prices or how to explain housing prices. So I is just going to be, housing for the price of sale 1 is going to be equal to all this stuff. We're going to plug in all these values for X. The sale of house 2 is going to be plug in all these things for X, but using the second home sale, right? So Y is going to be the outcome. Let's call it sale price. These X's are going to be the information, like I said before. So for example, this might be square footage. So X1 is going to be square footage of the house, of house I. And let's really just kind of focus on these betas first. So these betas are going to be some true parameter. They're going to be some sort of marginal impact of this variable, X, on Y. So in our example, we have square footage of the house. So suppose the house is 1,000 square feet, and the sale price is whatever the sale price is. Well, beta is going to be the impact of what happens if I increase my square footage from 1,000 to 1,001. How much more money is my house going to sell for, keeping everything else constant? So keeping the same number of bedrooms, the same number of bathrooms, the same everything. But what's the impact of just square footage alone on sale price? So these betas there's going to be a true parameter estimate. If we sold all the houses in the universe, in the world over time, right, we would get some sort of measure. There would be a true beta here. But we don't have every housing sale in the world. Rather, what we have is a sample, like 5,000 houses, right? All the houses sold last year in Morgantown or something like this. So we're going to estimate this using our data. So we're going to be able to take these parameters as beta 0, as beta 1, all these marginal impact parameters, and we're going to estimate them. So what we're going to do is, instead of saying, okay, I'm going to run my regression, running my regression is going to give me these parameters. When I run my regression, it's going to tell me what this estimate is. And then we're going to write that with beta with a little hat on it, a little caret on it. So here's a little picture of it. So this is the true beta. So what true beta would look like. And here's what beta hat would look like. So the estimated beta. So when we run regression using our data, we're going to try to get this, but we're actually going to have this. So the point is that we want the expectation or the average beta. If we did this analysis over and over and over again with different data, we would want the average beta hat to equal beta. So we're going to kind of talk about probability theory a little bit, and why it's so important in econometrics. So first, we're going to go kind of way back, and we're going to talk about just a statistical experiment. So this is going to be a well-defined set of possible outcomes known as a sample space. So for example, these are all of the possible outcomes. If you roll a die, you would have 1, 2, 3, 4, 5, 6. If you're flipping a coin, it would be 2 outcomes would be heads or tails. If you flip 2 coins, your possible outcomes would be heads, 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 tail, 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 or tails, heads, right? And this is called random because it has more than one possibility that we can't know before we run the experiment or before we do the thing. If I only had black shirts and I told you every day I wear black shirts, it's not a random experiment. It's not a probabilistic event. It's just me wearing a black shirt all the time. It's only one outcome, and it happens 100% of the time. So the probability of an event occurring is going to be the likelihood that some specific subset of this sample space occurs. So for example, if you flip a coin, what's the probability that you get a heads? That would be 1/5. We all know flipping coins. So for this one, we're going to say, okay, what's the probability of getting at least 1 tails? So that's going to be 3 possible outcomes that match your description out of 4 possible in the sample space. So the probability for this is going to be 3/4. And the probability that a likelihood event will occur, number is at 0 to 1. So you can have a bunch of probabilities of 0. You can also have one thing with a probability of 1. So the sum of all probabilities in the event space must be equal to 1. So I can't have a 2/3 probability of getting a heads and a 2/3 probability of getting tails. That would be more than 100% or more than 1. It has to be equal to 1 when you add them all up. Okay, conditional probability is something we talked about in Econ 225, or at least I hope so. You should probably recognize it as Bayes' theorem. So it's pretty much just saying, what's the probability of some event given some extra information? So for example, the probability of getting COVID might be 3% or some number like that. But if I give you extra information about myself, say I went to a party last week, then that would mean my probability of getting COVID is probably higher, right? Intuitively, you just know that conditional probability. You're saying to yourself in your head, okay, well, the probability of getting COVID is this, but he's given me extra information to update my prior belief being the baseline probability of getting COVID, given just randomly out of a hat. Going to a party increases those odds. So you're always doing it intuitively, but there's mathematical formula behind this to kind of explain it. You can go through the example by yourself. So these events that occur in real life, for example, getting COVID, not getting COVID, how sick I get, right? They're outcomes. They're events in the sample space of things, but we can't really just analyze like how sick I got. We can't say someone got sick bad, someone got sick normal, and someone didn't get sick at all, right? We want to map these outcomes to numbers so we can actually do analysis on them. Like an example, I think this last example is pretty good. Whether the Federal Reserve lowers interest rates, leaves these rates unchanged, or raises them. So these are 3 possible outcomes. This is the sample space of lower, do nothing, or raise them. Well, one of these events, we have to map them to numbers so we can analyze them, right? So we can, lowering interest rates, we can count as a -1, leaving them unchanged can be a 0, or raising them can be left as a 1. So we use these variables, these random variables to convert real life into numbers so we can analyze it. And then it is up to the econometrician or us to interpret those numbers, those numeric results back into the real world so we can talk about it a little bit more efficiently. So a probability distribution is all of the likelihoods of all of the occurrences. So in a dice roll, you have 6 possible outcomes. Each of them are the same amount of, or same level of likelihood, or the same probability. So they're all about 1/6. Usually what we do is we make these distribution plots where we plot the outcome on the x-axis and the likelihood or the probability on the y-axis. So for example, this would be like a bar graph. It would be 1 with a line about 1/6, 2 a line, 3 a line, 4 a line, 5 a line, and it would all be the same height. So there's 2 types of probability distributions in the abstract. There are discrete distributions and there are continuous distributions. So discrete distributions they take discrete random variables. Discrete random variables are counting numbers, things you can count and not have fractions of. So an example, or an economic example, would be the number of consecutive quarters of negative economic growth. If you have 2 or more consecutive quarters of negative growth, you are in a recession. So it's important to track these counting numbers, these counting quarters, right, of negative growth to tell whether or not we're in a recession and if policy needs to be taken. Another example, a little bit more non-economic and a little bit more real life, would be the size of shirts, right? So if we do one of our random variable mappings, if we take, say, extra small, we count that as like a 1, we count a small as a 2, we count a medium as a 3, and so on, we're going to have some sort of distribution, like a medium or a large in America might be way more popular than an extra small or an XXL. So we're going to have some sort of bump in the middle there that's going to look very popular, right? So it's not going to be this flat 1 6 1 6 1 6. It's going to be a distribution. It's going to be a little bit more uneven. Continuous distributions, this would be something that you can have fractions of. So any number that you can kind of go in between. So for example, the temperature or your height, right? The temperature can be 85 degrees. It can be 86 degrees. It can be 87 degrees. These are all integers. But it could also be 85.5 degrees, 85.3 degrees, 85.45 degrees. It can be any number in between these integers as well as the integers themselves. So an economic example would be the federal funds rate. So we were talking about the Fed deciding to raise or lower their interest rate. Well, the federal funds rate can be anything the Fed wants it to be. It can be 0, it can be 1, it can be 2, but it can also be 0.3, 0.4, 0.9. It can be anything it really wants it to be, even in between integers. So some famous distributions, a famous example of a discrete distribution specifically, is the Bernoulli distribution. So your outcome can have a 1 or a 0. So for example, it can either rain today or it cannot rain today. I can have eggs in the morning for breakfast, or I cannot have eggs in the morning for breakfast. These things will have different probabilities, but the other thing happening has to have 1 minus that probability. So for example, if I have eggs 10% of the time for breakfast, then I have to have something else other than eggs or no breakfast at all. 1 minus 10%. So that's going to be 1 minus 0.1, 0.9, so 90%. So they have to add up to 1. So this is a pretty common thing that we have in economics. So for example, you might want to look at, did this person get a raise? And you want to look at, well, are they a man or a woman? Are they, how much education do they have? What race are they? And you can have that binary outcome. So instead of having a housing price, right, you can have a 1 or a 0. Did this person get promoted? Did this person make the Hall of Fame? You can do all kinds of things like this. Okay, a famous continuous distribution is the normal distribution. So this is the formula for the normal distribution. There's 2 parameters, mu and sigma. So this is going to be the average and the standard deviation. This should have been talked about in Econ 225 ad nauseum, but probably not too much of this formula, probably just a table where you had to look up z values or t values. That all comes from the normal distribution. So a question might be, well, let me keep going. So this is the normal distribution that you should be pretty familiar with. So you have this bell curve with a mean of mu, and you have these standard deviations. As standard deviations grow, these specific percentages of data lie between them. This is exactly from the z table. but Z had a mean of 0 and a standard deviation of 1, right? So between -1 and 1, you had 68%, something like this. And then there are a finite other number of an infinite number of probability distributions. You could have the Bernoulli, the normal, a Poisson distribution, chi-squared distribution. There are tons. So in econometrics, we use these things to approximate reality. So for example, we will use the Bernoulli distribution to estimate binary outcomes, right? So did somebody get fired or something like this? Or we'll use a normal distribution in terms of maybe we wanted to predict somebody's height, and we're going to assume that the distribution of height is normally distributed. Something like this. Now, you might think, a question might be, well, why do we really care about the normal distribution, or any distribution for that matter? And the answer is because of the central limit theorem. So the central limit theorem, or the CLT, is super important in statistics and econometrics because we're estimating those betas. So if you remember, the central limit theorem says that as your sample size grows, the distribution of your averages, the distribution of your estimates, will approach normal distribution. Regardless of the underlying distribution of data, the averages will approach normal distribution. So in other words, if we want our estimates of beta to approximate a normal distribution, if we run this analysis over and over and over again using different data, we want to make sure our estimate of beta approaches the true beta, which we'll never observe, but we're hoping that by doing it over and over again, we can approximate that true beta and really understand the data generating process behind everything. Now, this is not to say that other distributions are not important. They are, because there's all kinds of other issues that come up. But the CLT is one of the foundational pieces of econometrics, and it's super important to know. So we're going to talk a little bit about expected value and estimating betas and stuff like that in a bit. But essentially, what the regression model we have here is just a conditional probability or a series of conditional probabilities and expected outcomes. But yeah, we'll talk about that more next time.